Okay. Good afternoon. We are Team 7, conformed by Marco Barreto and Gary Lara. We're going to talk about our project, which is water pollutant agents. Next one. This project is about the Zapotlan Lake, which is located in Jalisco, in Zapotlan El Grande municipality. Is the second largest lake in Jalisco, and it is monitored by the Jalisco State Water Commission in 4 sampling points along the lake. Next one, please. There are so many water quality variables that allowed us to know how a water body like a river, a lake is, and if it is healthy for the population near or also for the biodiversity. Among these, we have total suspended solids, chemical oxygen demand, phosphorus and nitrogen content, among others. And these are often measured in authorized laboratories from samples taken from the lake. Next, please. Well, for our project, we have data from September 2009 to April 2018. These data sets includes information of 3 numerical continuous water quality variables, which we are going to explain later. And the purpose of obtaining this data was to analyze which groups of pollutants exceeds the permitted levels and associated with different activities carried around the lake and some milestones, such as, for example, the change in type of agricultural activities and also the introduction of water treatment plants. The next, please. Well, our variable definition, we have the total solid, which is the amount of solid mass per liter of water. This is relevant because the solids are related with sludge deposition, pathogens protection, among others. We have the total nitrogen variable, which is the amount of nitrogen per liter of water. It is related with a phenomenon called eutrophication, which is the overpopulation of algae species in a water body, which tends to sequestrate all the oxygen available. And this affects all the, for example, fishes that lives in a water body. The biochemical oxygen demand is the amount of oxygen required to chemically stabilize the matter. This is related with the oxygen availability for the animals that live in the lake. And we have other 2. The first one is lake locations, or the sampling point of the lake. We already said that there are 4. This is relevant since each lake or board has a contact with different human activities, and also the time, which is the period of the measurement. This is relevant because there are some milestones that we already said, like the introduction of treatment plants and the change in the type of agriculture. The next, please. Well, we have, as we said, 3 continuous variables, which are biochemical oxygen demand, total solids, and total nitrogen. These are continuous and generated by measurement of natural values. Without further analysis, we can consider that they have a normal distribution. They follow a normal distribution, sorry. But we will perform goodness of fit test to see if it's real distributions of each variable. And also we have 4 categorical data, which are the lake locations, the sampling points. It has 4 levels, a level per sampling point, 61 observations per one, and all these categorical variables follows multinomial distribution. We assume that, and we have 3 different time categorical variables. The first one, which is divided in 4 levels corresponding to the seasons. And the second and third one distributed in 2 range of time, which corresponds to the milestones of change in agricultural activities. This is the time 2, and the time 3 corresponds to the introduction of treatment water plants. The next one, please.
Next, we have the summary of the data. So we have our 3 variables here. And for the BOD, we have the minimal values, the mean, and the maximum values, as well as for the solids, the mean, the max, and the mean. And for the nitrogen as well, we have the summary of the data. In the next one, we can see the scientific hypothesis that we have 5 of them, which are the lake location has an effect over the biochemical oxygen demand variable, because we have 4 different stations to take that variable from. The second one is the season, that we have autumn, winter, summer, and spring, which is the time 1 categorical variable. And this has an effect over the total nitrogen variable. The third one is the time over the years, that it has an effect over the biochemical oxygen demand variable. The fourth one is the agricultural activities, which is the time 2 categorical variable around the lake, and it has an effect on the total solids and total nitrogen variables. And the fifth one is the introduction of the sewage treatment plants around the lake, which we take it as a categorical variable time 3. It has an effect over the total solids and biochemical oxygen demand variables. Next, we have the statistical hypothesis, which is Gary is going to explain them.
Yeah, thank you, Marco. The first one is the hypothesis that there are no significant difference between the average biological oxygen demand among the lake locations. It is just a comparison of means. The null hypothesis says that there is no difference, and the alternative says that at least one is different. The next one, please. The second one is that there are no significant difference between the average total nitrogen concentration among seasons. It's the same as the previous one. We have the average of nitrogen concentration in each season, and this is the null hypothesis, which means they are all equal, and the alternative is that at least one is different. The third one is that in order to see if the biological oxygen demand it changed along the years, we will seek to perform a polynomial regression of n order, and our new hypothesis will be that if the nth term it's equal to 0, this is the null hypothesis, then the polynomial does not fit well for the given data. But if it's different from 0, then the polynomial fits well. The fourth one is that, next one, please. The fourth one is that there are no significant difference between the average total solids concentration among periods with different agricultural activities. Here, let me to explain. The change in agricultural activities, it is contained in the categorical variable named time 2. Time 2, as we already said, has 2 levels. One level is from 2009 to 2014, and the second one is from 2015 to 2018. These 2 time frames are, well, time frame 1, time frame 2. We were going to calculate the average of total solids concentration in the period 1 and in the period 2. Why? Because of 2 periods. Because in the middle, in 2014, their agricultural activities change was introduced. So we are going to see if the average total solid concentrations have been affected from that change. The statistical hypothesis 5 will be the same, but with the total nitrogen concentration. The new hypothesis, I already forgot to say in the previous one, but is that the average of this variable, it's equal, they are equal, and the alternative hypothesis that they are different. For the sixth statistical hypothesis, we have that there are no significant difference between the average total solids concentration among periods with different presence of water treatment plants. This functions very similar to the fourth and fifth statistical hypothesis, because they are working 2 time frames. We have time frame 1, which is before the introduction of water treatment plants, and we have the time frame 2 that is after, and we're going to see if this variable, the average of this variable, it's different between those periods. So the new hypothesis is that is that they are equal, and the alternative is that they are different. The seventh statistical hypothesis is the same that the sixth, but with the biological oxygen demand. And there are the null and the alternative hypothesis pretty the same, but with another variable.
So we employed the R risk distribution package in RStudio to fit our 3 response variables. The first one is our BOD, and the software suggests that it follows a gamma distribution with this lowest score, which is 660. And for the next one, which is the TS, it follows a logistic distribution. And for the next one, which is the TN distribution, which it follows chi-square distribution.
Yeah, for the parameters identification, in order to test our statistical hypothesis, since they're all mainly all comparing the means, we need to estimate the mean, and also to perform the test, obviously, and also the variance or the standard deviation to test if some of the requirements, such as variance homogeneity, are fulfilled. For the gamma distribution, the mu is alpha over beta. These are from the parameters of gamma distribution. For the chi-square, the mu is equal to k, also a parameter of the chi-square distribution. For the logistic, mu is mu. It is the next one.
And well, for this one, in the presentation, we are going to focus on the BOD, the biochemical oxygen demand, to work on, and it follows a gamma distribution. From literature, this distribution is known to be widely used to fit variables such as environmental, meteorology, and climatology, which fits our needs perfectly. So we have the PDF function from the gamma distribution. And from this function, we know that the parameter beta is called the scale parameter because values other than 1 either stretch or compresses the PDF in the x direction, as we see in this graph here. Well, looking into the prior, we see that since our current data, the one in the middle, has a gamma likelihood, its conjugate prior, it's a gamma distribution as well. So meaning that if we know that the prior follows a gamma distribution, the posterior will be a gamma distribution as well. To obtain the prior, we use bootstrapping from our current data to determine if the parameters alpha 0 and beta 0. Then our posterior will have these new parameters obtained from the prior, which is alpha 0 plus n alpha. And for beta, we have beta 0 plus the number of observations of 1 over x y. And then we have our prior distribution on the left. Then we have the gamma likelihood. And finally, we have the gamma posterior, which has a shift to the right.
Well, for the Cramer-Rao lower bound, first we started from the definition, which is 1 over n times the Fisher information matrix. Applying the Fisher information definition, which is the second derivative of or parameter of the log likelihood function, we obtain that for the gamma distribution with the fixed alpha parameter, with the alpha parameter fixed, so we are only derivating for the beta, and we obtain that this is minus expected value of minus alpha over beta squared. which applying the expected value led us to the Fisher information is alpha over beta squared. Applying the Cramer-Rao definitions, which is only divided 1 over n by this, we obtained that the Cramer-Rao lower bound is beta squared over n times alpha. And we calculate this and do the graph with the code that we are going to show us in a few moments. And our Cramer-Rao lower bound is of 0.0013. You can see the red line below. And we do the computation of 1,000 times of resampling to see how the estimate varies, and this is the graph.
So speaking now about the permutation or the Fisher exact test, we consider that only our BOD data contains 224 observations, and we use random sampling to reduce it, the data set, and work with less observations. Then finally, our approach is to compare means between two different populations. And given these statements, we are not candidates to use the Fisher exact test. So we are in R here, and we're gonna take a look in the prior code. From the prior, we are gonna see the likelihood, and we're gonna see how the posterior is calculated. So we look into our data from here, and we obtain only the BOD data. We do goodness fit, and we obtain that the gamma is better fits this distribution. And then we graph it to know that our alpha is 3.07 and our beta is about 0.04. This is a scale, and we obtain it with the rate, just to make that clear. And later on, we make a resampling from the original data to obtain the prior. That's how we are building it. And then we obtain the alpha, which is the shape, and we obtain the beta, which is the rate. And then we plot it, and we obtain this prior density we have here. And for the posterior, we calculate the new parameters as we see in this block code, where we have alpha 0 plus the number of samples and times the known alpha parameter that we know. And from the shape, from the rate, I mean, we have the beta 0 from the prior, and we have the sum of 1 over xy, and we calculate this and we plot it, and we obtain the new posterior, which is a shift gamma distribution to the right.
Well, for the Cramer-Rao lower bound graph, we read our data. We are focusing in one variable, which is the BOD, that we already explained, that follows or fits a gamma distribution. For the since BOD has a size of 61, we put a n of 40 to do a resampling. We calculate this, which is 0.0013, and then we use the optimize function in a 1,000 times iteration. We sample this variable. We optimize the gamma distribution, well, the beta parameter of the gamma distribution. We obtain its minimum. From this rate, we obtain two variables, the minimum and the optimal. and we subtract from this fixed variable of beta the minimum obtained here in the optimization, and this is all the point that we see here, and then we plot it. As we already show, this is how it looks. This is the Cramer lower bound, and these are all the points. Well, that's all for the team 7. Thank you for your attention.